Dear students, today we will discuss the topic Fourier series. In this topic, first of all, see the definition of periodic function. What are periodic function? When we change the variable of the function theta from theta to theta plus alpha and the value of the function remains unchanged, then we say that the function is periodic and its period is alpha. For example, we have a function fx. If f of x plus alpha is equal to fx, where alpha is any least positive constant, then the function is called periodic function and alpha is its period. For example, we have a function sine theta or sine alpha. We know that after a angle of 2 pi, its value repeats, means sine alpha plus 2 pi is always equal to sine theta, cos theta plus 2 pi is always equal to cos theta. Then we can say that these functions are periodic functions and their period is 2 pi. Sine theta, cos theta, secant theta, cosecant theta, all are periodic function and each is of period 2 pi. In case of tangent theta, the value of the function repeats after an interval of pi. So we can say that its period is pi. Tan theta, cot theta are also periodic function with period pi. Next we have some important results. For the function sine n theta and cos n theta, the period is 2 pi divided by n. These are also periodic function as we see in the last slide of periodic functions. Similarly, sine pi theta by L, cos pi theta by L, these are periodic function with period 2 pi divided by coefficient of theta. This comes from the above result. Next important result is sum of a number of periodic functions is also a periodic function. If alpha 1 and alpha 2 are periods of two functions, say fx and gx, then the period of this function a fx plus b gx, where a and b are some constants, is the LCM of alpha 1 and alpha 2. For example, we have a function 2 cos x plus 5 cos 2x minus 3 cos 3x. Now, from the above results, the period of the function cos x is 2 pi, cos 2x is 2 pi by 2, cos 3x is 2 pi by 3, means 2 pi, pi and 2 pi by 3, and LCM of these three numbers is 2 pi. So, the period of the function fx is 2 pi. Next we have some important results of definite integration which we read in the class plus 2 standard. You all know about these results. First result is when we integrate a function sine nx from alpha to alpha plus 2 pi, its value is equal to 0 when n is not equal to 0. We can easily prove this integration of a function. Similarly, we have another result. Integration of the function sine mx cos nx from alpha to alpha plus 2 pi is also 0. This is possible only in the case when m is not equal to n. Third one is the integration of the function sine nx cos nx from alpha to alpha plus 2 pi is also 0 provided n should not be equal to 0. We have to remember all these results to proceed for the topic Fourier series. Another result is integration of the function sine square nx from alpha to alpha plus 2 pi is pi provided n is not equal to 0. Similarly, the integration of the function cos square nx dx is pi for n not equal to 0. We have some another results which we require further in solving the Fourier series of the function. integration of these two functions is required. Another result is, for a periodic function of period 2 pi, we have the integration of the function fx from a to b is always equal to integration from a plus 2 pi to b plus 2 pi. Both these two integrals are equal. Similarly, we have to remember this result, and third one is also important. Next, finally, we have the definition of Fourier series. What is a Fourier series? Any series of this form, a naught by 2 plus a1 cos x, b1 sin x, plus up to so on, an cos nx plus bn sin nx, or in short form, any series containing terms of this type is called Fourier series. And the numbers a naught, a n, b n, these are independent of x, and these are called Fourier coefficients. We have some results about the Fourier series. First one is, when function is an odd function, then the value of the Fourier coefficient a naught is always equal to 0. This result comes from the formulas of definite integration, which we have discussed in the previous slides. Second one is, as we know that the cos function is always an even function, so fx cos nx will be an odd function, as fx is taken as an odd function. Then the value of the coefficient an comes out to be equal to 0. Third one, we take the value of the Fourier coefficient bn. As we know that sin nx is an odd function, so fx sin nx will be an even function, so value of the Fourier coefficient bn comes out to be equal to this term. So in this case, we conclude that when fx is an odd function, then the Fourier series contains only sine terms, as this Fourier coefficient is equal to 0. These are important results which we require for solving the questions regarding the Fourier series. Next one is the case when fx is an even function. In case of even function, the value of the a naught is equal to this integral. We can calculate this value by substituting the value of the function fx. As cos is an even function, so this function is also an even function, so value of the Fourier coefficient an comes out to be equal to this term. As we know that the sin nx is an odd function, therefore the function fx sin nx will also be an odd function. So in this case, the value of the second Fourier coefficient is equal to 0. So in the case of even function, the Fourier series contains only cosine terms. Next, we have an important theorem regarding the Fourier series, and this theorem is named as Fourier series and Fourier coefficient theorems. Its statement is, let the series a naught by 2 plus summation an cos nx plus bn sin nx be uniformly convergent in this interval, and the series have the sum fx, then an is equal to this integral and bn is equal to this integral. As it is given in the statement that the series fx is equal to this is uniformly convergent in the interval alpha to alpha plus 2 pi. As the series is uniformly convergent, so its term by term integration is possible. Take integral on both sides from the interval alpha to alpha plus 2 pi. The first term becomes a naught by 2 integral alpha to alpha plus 2 pi 1 dx plus summation n is equal to 1 to infinity. We take the integral of each term separately. As we have these results in the previous slides, so both these terms are equal to 0. So from this calculation, we find the value of the Fourier coefficient a naught is equal to 1 upon pi integral alpha to alpha plus 2 pi fx dx. Then again we take the concept of uniformly convergent. This is the definition of uniform convergence. where Sn is the nth partial sum of the series. Nth partial sum means first sum of first n terms of the series. Then fx cos nx minus Sn cos nx is equal to this term. Then separate the modulo of both these terms. As we know that modulus of the cos function is always less than or equal to 1, so this term becomes less than or equal to this one. From the above step, this term is less than epsilon. Similarly, we comes out with the result that mod fx sin nx minus Sn sin nx is less than epsilon. That means if we multiply the series 1 by cos nx sin nx, then the resulting series is also uniformly convergent. So term by term integration is possible. So if we first multiply the given series by cos nx on both sides and sin nx by both sides, then integrate these two equations as in the previous case and use the results of definite integration, we comes out with the result that an is equal to this value and bn is equal to this one. This, for we take the example of the first equation, you can then solve the second one similarly. When we integrate this term from alpha to alpha plus 2 pi fx cos nx, when we integrate this term from alpha to alpha plus 2 pi, then alpha to alpha plus 2 pi cos nx dx is equal to 0. So this term becomes 0. Again, in this case, the term this one becomes 0 and we remain with this one, this term an alpha to alpha plus 2 pi cos nx we are taking the value for m is equal to n. As we know that for the value m not equal to n, this integral is 0, so we are left with this term only. From this relation, then from the formulas of definite integral, this integration is equal to pi, so this term becomes pi, and those from this equation we find the value of an. Similarly, when we take this fifth equation, then we find the value of bn. We are using here the formulas of definite integration. Then further theorems we will discuss in the next lecture.